5.4, you have, checking, you have extension for this homework due Monday. Sunday, due Sunday. So very interesting idea. What if we know the integral from a to b f of x, one of the application of the integral is to find the area below the graph of f of x from a to b. Well, what if, say the area represents the number of patients in the hospital, and I want to see it from today in the months. That's going to be this area. That's total number. It's like fancy addition, it's fancy summation, right? I'm going to sum up all the patients in the hospital from A till month 1. So say December. Oh yeah, happy 1st of December. December. Then I change my mind and I want to check January. That's going to be here. Then I change my mind. I wanted to do February. It's going to be here. So what if sometimes you don't want to fix one of the limits of integration? What if you want it to be moving? That means x becomes a variable. And x can move to the right if I want to increase the area, and to the left if I want to decrease the area. So that's pretty cool. You fix one of the endpoints, and then you move another one. And this is how it looks in the cool animation I found. Here you go. One variable is fixed, and another one is moving left and right. So it means it's keep changing how much area I want to calculate or how much sum I want to include. So in this case, do you recognize the function in blue? Looks like sine. So sine, integral of sine from 0 to pi will be all this upper half. Integral of sine from pi to 2 pi will be lower half. But what if I fix it from 0 and the other one is keep moving? Well, the red function is result of integration. The area is positive, but then the red function is increasing. The more negative area we're adding up. The more area, total area decreases because one is positive and another one is negative. So increasing, and then negative area starts killing the positive area, and it all shrinks to 0.
So we're treating area under the graph as
negative
area?
Yeah. So positive and negative.
Would there be a question where they're asking us, like, what's the total area under the graph treating the negative area?
Yeah, I will not do tricky questions on the exam like that. And in Calc 2, we're going to make it so much easier. You don't have to even be bothered with a sign when we learn area below, between graphs. That's going to be the first 2 weeks, the first months of Calc 2. But yes, you should imagine that you're digging a pit, and when you're digging it, the area below the graph is empty part, and right before that there's now like a little hill of dirt. So positive and negative. If you move all the positive down to the pit, it adds up to 0. So that's kind of how you can see. That's a pretty phenomenal idea that you can actually treat one of the limits of integration as a variable x. Here you go. And here's the interesting idea which I mentioned. Integral from 0 to 2 pi of sine. That is going to be a finite number. It's a number, some kind of area. However, if I change integral from 0 to x, now it's a function. So now the area will depend on the stopping moment of x. For x equals 2 pi, it will be the previous integral. For x equals 7 pi, it will be different. For x equals 55 pi or minus 38 pi, it will be different. Thus, integral from 0 to x or from a to x gives you a function. That's called area function. Here you go. You can write it down, or you can just know that I give you those notes anyways. If f is continuous, then the area function means it depends on something, of f with left endpoint being fixed is a of x, let me zoom in, a of x, integral from a to x, ft dt. And you see they're choosing t instead of x. That doesn't matter. T in this case is a dummy variable. They just don't want to be confused with x in this case. X is the unknown upper limit of integration. It can be increasing or decreasing. T is a dummy variable. Dummy variable, it means we're just using the name, dummy variable. You will see it a lot in computer science, and also called a dummy variable, a counter, for example. And this is going to be a function, the function that depends on the choice of x. See, its area should be a number. I will keep saying it all the time. And suddenly it's a of x, because it makes sense. I want to find the volume of this room. Well, it depends when I'm gonna stop the sum of the limits of integration. From here to there, from here to farther, from here to the end. Thus, it's a function, depends on my choice. The area function gives the net area. You can even call it net area. NET, net area function of the region bounded by the graph and the t-axis on the interval from a to x. So let's practice to see, and surprisingly the first example is not even that important for your homework, but it's kind of more important for understanding what's happening. But luckily, at least it's also nice practice of integration techniques. On the exam, you need to show us you're very good on integration differentiation. You're not supposed to go to anything if you're not good with integration differentiation. So, integral of 2t plus 3 dt. What is antiderivative of 2t? Everyone can just say out loud. 2t squared over 2, right? T squared over 2 times 2. Let me write down in general, but then you get used to it and you know it cancels out. You can ask yourself what gave you 2t? T squared gave you 2t. Plus 3. 3 becomes 3t. Ask yourself what gave me 3 after differentiation? 3t. Bar 2x. And the idea is the same. Let's plug the top. Everywhere I see variable t. Variable t is my dummy variable. And then variable x is my b that is not fixed. It's going left and right. It's going to be x squared plus 3x parenthesis minus. So I'm plugging top t equals x, plugged everywhere. Now plug the bottom, and the bottom t is 2. 2 squared plus 3 times 2. And don't forget the negative sign, because we're scanning from 2. Scanning means difference, right? From your head to the floor. So that's your height, how tall you are. It will be, say, 6 foot minus 0, minus floor. And that's the difference. So don't forget the negative sign. And that's the answer. If you simplify it, it becomes x squared plus 3x minus 10. The area for the first time is not a number. But that means if I fix x to be 7, then it will be integral from 2 to 7, and that's going to be the answer when I plug 7 into x. If I decide to do from 2 to 0, the answer will be minus 10, and that's how you know it's wrong. Because from 2 to 0 will give you a negative result. Why would you go to the left? I mean, you can go to the left, but the answer will be negative for the area. And so on. So it's a pretty cool idea. Yes?
We've made the lower limit or the lower end of the interval constant, and then the variable is the upper limit.
Yeah.
Are there situations where it's...
Oh, very good question. The question is, we keep mentioning that we have integral from a to x. Lower is fixed, upper is a variable that's going left to right. Can we have x to b? Does anyone can try to figure out? Ideas? Can we have that? Any ideas? We can't? We can. How? Do you know? Can you guess?
I mean, it's the same process except we plug in x.
Yeah, it's the same process. You can see it as, you can always flip it with a negative sign to be b to x, and now it becomes the same thing with a negative in front. Yeah, it's a very good point. Exactly. So that is the idea of a net area. Also very interesting. Let me draw a graph for you to show you that it is indeed very interesting. Here's the graph, x to y, and I'm gonna draw what the area below what we're looking at, 2t plus 3. Draw a line, 2t plus 3. At 0, it is 3. At 1, it is 5. And that's how you draw a line, right? You need just 2 points. 2t plus 3. And then they ask us to find the area from 2 over here to x. And x can go to the left and to the right. So we never fix the upper limit of integration. Here is the area. And we found the area. It is a quadratic function that depends on the input of the choice of x. So question for you. Okay, not only is trapezoid, by the way. It's actually trapezoid. But question to you. What is going to be if I choose some curious examples? Note. What is going to happen if I want to find area when x is 2? Then the integral will be from 2, that was chosen originally, till 2. Guess, what is the answer? Why? How do you know?
Because they're going to have the same value.
The same value.
The same value minus the same value.
Yeah, it's going to be same value for a and b. There's so many ways to explain it. Either you remember the properties of integral. Integral from a to a is 0. The way it's designed is, yeah, like you said, whatever you plug will be top, whatever you plug will be bottom. It's the same number. And graphically is my favorite way. Graphically, it means this is the height of the rectangle we keep looking. Because you remember we have like those rectangles and stuff, like, or trapezoids. So here's a rectangle. The height is fine. That's the height of the function. But the width becomes 0. Because from 2 to 2, if it's even from 2 to 3, the width is nice. But if it's from 2 to 2, the width is 0. What kind of rectangle has width 0? The one that has 0 area. But if you plug it into the function a of 2, it becomes 2 squared plus 3 times 2 minus 10, and indeed it is 0. So it makes sense. Like all of this makes sense. Good? Here's your better graph if you want, blah, blah, blah. And again, I'm gonna impress you with this cool animation. See? So it depends on my choice of the limit from the right. Let's not say that. Upper limit of integration. From 0 to 2 pi over 2, this is the area. The area is positive. The red function is going up because it's a function of x. That's the answer. But then I start adding negative areas, and the function is decaying, 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 and at the end, it's 0. And you can check integral from 0 to 2 pi of sine is indeed 0. Now we're actually going to do things that we want to test you on the test. And we want, and your homework. That was just kind of pre-knowledge. Question, how fast? How fast this function a of x, which is net area function, how fast is this function is changing? Interesting. That is true. So I just showed you there was a function in the red. The area is increasing, increasing, decreasing, decreasing. So in our case, the same thing. In our case, the more I add on the right, the bigger the area becomes. Because unlike sine, it never goes down, right? So the more I add, the more it keeps going. That means the function that represents how much area is accumulating is increasing. The function is increasing. That means the original function. Now that means its derivative is positive. So how can I answer this question? Mathematically, we do what? Differentiating. Exactly. Find a prime of x. Well, it's easy to find. So from the previous example, we're going to have a prime of x will be 2x plus 3. That was easy. I just differentiate the polynomial I had with x squared and stuff like that. What if you don't have that function? What if you did not integrate? And what if you don't want to integrate? Then let's Yes, what if you did not integrate to find derivative after that? Well, let's find a derivative, and that's, let me show you my notation, and then you will see book notation. The original integral was from 2 to x, and let me check what was inside of the integral. 2t plus 3. Look at this, it's the same function. 2t plus 3, it's the same that I just found. Just the variable is different, 2t. What if I want to differentiate? Let me put in red color. No, let me put in blue. Prime. Why is it the same function? What do you think? Why the answer became 2x plus 3? Yes? No? You was just stretching? No, you know it. Yeah, go.
It's the same because the x is just the integral, so when you're doing the derivative of it, you're going back to the original function.
Exactly. There was an integral, and we're differentiating the integral. So we're going to the original function. Mind-blowing, right? No, it makes sense. It's not supposed to be like, wow, that's so crazy. You're undoing the process of integration by differentiation. So it's like you have velocity. And velocity is the integral of acceleration. And now you go back to acceleration. You differentiate the velocity. Well, it's not that simple if something has chain rule in it. Of course, nested functions. So let me make a note. In pink, I guess let me put everything in pink. In pink, that is an integral, or integration. And in blue, that is differentiation. So we're differentiating the integral, we're undoing the process. How fast does this area accumulate? Let me show you the animation again. How fast does this area accumulate? It accumulates as fast as the original function. What is the original function on this graph? The blue one. The blue function is the one that goes inside of the integral. What's the area below the graph of the sine? That's the one in blue. So how fast does this area changes? It changes sine fast. And do you see, this is like a whole cool idea here. That's one I have to say, it's pretty cool. So the red function is the area that accumulates. How fast does it change? It changes as fast as the original function. And it does look like cosine, which is derivative of sine also. Do you see? So it has all those connections. Sine and cosine give you each other. Area accumulates. Area on the top matches with the area at the bottom. If they completely fill up, gives you 0. All of those things totally make sense when you add up together the knowledge of differentiation, integration, trigonometric functions, and changes, which is differentiation. Anyway, you have those. I don't want you to write down too many things. Write down 2 formulas. This one you already have it. I guess you don't have to repeat it. Integral A of x is called net area, total area. But the most important part is that upper limit of integration is not fixed, and x is running left and right from A to B, because everything is happening on the interval A to B. But what if now I want to differentiate it? If I differentiate all this result to answer the question, how fast does this integral changes? That means I'm differentiating the integral. And the answer will be the original function with the variable that is on the top of the integral. The variable must match this x. That's important. And I'll show you in a second why. Did you copy? And then I'm reminding you, this is what called Fundamental Theorem of Calculus Part 1. Part 1 is not as practically used as Part 2. So we always teach Part 2 first, at least in America. And Part 2, are reminding you, is this idea, top minus the bottom idea is what Part 2 is, connection between antiderivatives and areas or applications of integrals. Part 1 is this changing area or area function. That's how they call it. And now I'm going to give you cases. Case 1. So how to find derivative of the integral. Case 1, you just plug in. That's the easy one. So if I say find a derivative, and that's the notation in the book, and that's the popular notation, d over dx of what? Usually it's like dy, right? But instead of y, there's an integral from a to x, t squared plus 2t dt. What you do is you take this variable x and put it everywhere you see t. And the answer becomes x squared, plus 5x, x squared plus 5x. That only works if x is standing by itself and there's no troubles with this x. And I will tell you the thing about what kind of trouble there can be. That's the easy case. You will not have the easy case on the test, unfortunately. It's already there. It's already on the exam. We always have to put at least one problem. You will have one of the... Okay, that's the other one. What if you have to flip it? Because the integral is the same d dx, but it is from x to b. T squared plus 2t, or it was 5t. Can you fix to 5? I know I put 2. 5t. Then the answer will be minus. You change, and then you flip it. You flip the integral. And then you plug x, and it's going to be x squared plus 5x. But with minus. Does it make sense? You flip it. You must... Either you do it step by step or skip the step of flipping. Just put negative sign. And case 3 is the one we put in the test. I just kind of gave it away right away because that's the classic thing to give on a test. The case 3 is chain rule. Of course, chain rule always bring troubles. It's not too bad. You will, of course, the most important part, the computer decided to freeze. Probably I should turn this off. Good. Case 3 is the chain rule. Case. Your favorite chain rule. Those are my notes. I'm pretty sure in the book they don't do cases and they just like tell you, you have to figure it yourself because you're so smart. Just it's so obvious. So I always teach through cases. I think it's better. Find a derivative. Let me put it in black. Come on. Find the derivative from a to, guess what, x cubed. What? What if there's a function? What if there's a function hidden in the variable of integration? That's chain rule because it's a function inside of the function of the same t squared plus 5t dt. And that's the hardest part. You plug in and then you do times derivative of that function. So plug in this whole thing everywhere you see t, just like you did before, but now it's not like a simple case. So it's going to be x cubed, x cubed, parentheses, squared, plus 5x cubed. You're plugging in that function. And then you do times, that's when the chain rule happens. The chain rule says, don't forget to differentiate the function inside. And as you can see right now, the function inside is x cubed. Derivative of the function x cubed is 3x squared. That is the answer now. And you simplify and then get yourself the nice answer. In my notes, if you simplify it, it will be 3x to the 8 plus 15x to the 5. So the idea is, yeah. Yes, what's your question?
Should it be x at 6? X cubed squared.
Oh yeah, that's complete simplification. So it was x to the 6 times 3x squared.
Oh,
Yeah. Thank you. So that's like the final answer. I'm just skipping it for the time. So what I wanted to say is the steps, I have nice like written steps here, is plug in and multiply by the derivative. So plug in and multiply by, of course it's gonna shut down, by the derivative. Yeah, see the last class it says no, good enough, let's go home. Yeah, it completely restarted. That's fine, I understand. To be honest, I'm very compassionate to technology at the end of the semester. Like, you did good job. You did good. Next semester I'll have 2 classes in a row and I don't think it can handle 2 classes. So I will have to probably use a newer one. Do I own a newer one? No. So that might be a problem. So let's see. Oh, it erased all my beautiful phrase. Rude. Plug in the function, so the whole thing, and multiply by the derivative. And the last case, and I'll show you more example right now. The last case is not really something new. I will ask you right now, what do you think we should do? And you can get it. It's a very cool idea. Case 4 is, what if you have integral from x cubed to x, oh, let's do like not just polynomials, sine x, something like that. And they ask you to find derivative of that. And the function inside is, say, ln of x squared plus 5. And they don't use x inside. As you can see, it can be anything, just not to have the same variable. It's still dummy variable, doesn't matter. So here's what's happening. We're differentiating the integral of natural log of t squared plus 5 from x cubed to sine x. So we don't know how to differentiate the integral that has both limits of integration not fixed. Well, you break it then. Break it using knowledge that we can find the breaking point. So let's find a derivative. Let's find a derivative of the integral number 1. It's going to be from x cubed, for example, to 0. You're not supposed to choose a random one, but 0 is a popular choice. It rarely doesn't work if 0 is not in a domain. Sometimes it's like 1 over x. Good luck with plugging 0 then. Of this function plus 0 to sine. And then it takes you back to 2 previous cases. Case number 1, plug in, take the derivative. No, that's case number 3. And then case number 2 when you flip first. So let me finish this for you. The first case, I'm going to put minus sign, right? Because it needs to be flipped. If you see that a is not fixed, you need to flip it. And by flipping it, I will do minus sign. I will write down natural log of t squared plus 5. And instead of t squared, I'm going to plug x cubed. X cubed squared plus 5. And that is not the end. Times 3x squared. That's the first integral. Plus the second integral doesn't need to be flipped. It's from 0 to sine. So I'm going to do plus natural log of t squared plus 5 becomes sine squared. Sine squared. Sine squared plus 5. And that's not the end because it's not just x. It's a function of x. It's going to be times derivative of sine, which is cosine x. And that is the answer. So we have 4 cases. The case number 4, I call it the break.
So for case
Break and flip. Yes?
So for case number 4, instead of having instead of doing from one end to the other end, we're just picking a point in between them and going,
Yeah.
and then adding them together.
Yeah, because you need to have one point there that is fixed. If two keep moving, that makes two different rate of changes, right? So if I'm left side is keep moving with this speed and the right side is keep moving with this speed, and I'm talking about A and B, then there should be two different functions representing the speeds. That's need to have a break for one. This one moving with this speed, okay, that's going to be one derivative. And this one was moving faster, for example, that's going to be another derivative. And the answer is the sum. It makes sense, right?
Yeah. Are there any considerations when we're choosing the break?
Yeah, just choose 0 in. If we had more time, like we did in University of Utah, we actually explored that the choice have to be smart. But in your homework, 0 works all the time. I checked.
Okay.
Yeah.
Why is the first part negative?
Oh, the negative is, thank you for asking, because this is not good. This guy have to be from 0 to x cubed. So to fix that, I'm doing minus 0 to x cubed. Make sense? To flip it. So that's why I put here and flip. So let me make a good note. Yeah. Thank you. Flip. That makes a better note. So good question. Does it make sense? So at home, you just do, this homework goes fast, I can tell you, because you don't really calculate anything. You just keep finding, you just keep plugging things in your homework. And it will look odd. So let me do one example in 5 minutes. Example. Yesterday I was observing someone's teaching pre-calculus class, and the professor finished class 10 minutes earlier. 10 minutes. Like, I will never do that. We have 5 minutes, we're gonna work 5 minutes. Are you kidding me? 10 minutes earlier. I was so shocked about that. Why we're done? That's interesting. Anyway, so it was not yesterday, on Wednesday. If I want to find the derivative of a function, and it should be like 1 over a square root 1 minus x squared dx, and it's going to be from 7.3 to minus x to the 4. Yeah. And you're like staring at this. So on a test, you will stare at this integral. And you're like, oh, I know this integral. What's the integral of 1 over square root of 1 minus x squared? Arcsine. And we don't write arcsine here. And that's, I think, what the challenge is. We were forcing you to memorize all those formulas. And you finally did it. And you're so proud of yourself. Yeah, there's no arcsine in this answer. Because we are doing differentiation, integration by differentiation. So the function will be still 1 over the square root 1 minus, and x actually should not be x. That's not a mistake to make it x, because again, it's dummy variable, so it can be anything, but it's smarter not to write the same variable. So it's going to be input squared. My input is minus x to the 4, and guess what? Squared. So you see, it's not arcsine because we never integrated. We differentiating integration. Times the derivative of the function inside. And now you see it is a function inside. It's not just x. It's minus x to the 4. So chain rule says, well, since we differentiating, don't forget to differentiate the function inside because it's a Russian doll procedure. Or chain procedure. That's why it's called chain rule. And derivative of the function inside will be minus 4x cubed. And that is the answer. Interestingly, that nobody asked before, but usually students ask. Nobody wants to ask me what's happening with 7.3. So we completely don't care about the initial point. That's the thing. Because we're asking, when we perform the very first example, when we actually find the net area, of course it matters. The very first one, I plugged the top, and then I plugged the bottom, and the bottom was 2. And only because I plugged 2, I got the function that I have, x squared plus 3x minus 10. But if I'm undoing this process, I'm asking about the speed, how fast you were driving. And because it doesn't matter you were driving from this tree or the next tree, it asks about the speed. We don't care about the first limit of integration. That's how interesting it is. So 7.3 or whatever that number is, it's a constant. Don't be bothered. It's just have to be fixed. That's the only thing we need. So case 1 is the easy one. It's not on the test. That's too simple. Case 2, flipping, too simple. Case 3 is on the test. When you need to know what's happening with the function and the function inside. So x cubed have to be at the end differentiated. 3x squared. What do you think about this? It's very quiet. I guess I always know at the end people are very tired, so no judgment here at all. Good job, people. You survived all this long. Oh, we have a question. Yes.
Is that the end? Or do we...
Yeah, that's the end. You can simplify it if you want by putting it in one fraction. You survived, and I'm very proud of you. You will be taking tests. Okay, now it's too late. Now you have to come and ask. And I will see you on Thursday. We still have room reserved for the office hours right now, if you want to go and sit there. But I will be holding office hours for the online students.
I hope to get you for next semester, but if I don't manage, I really like you.